first one is
count the complete subarray in there. Okay. So you are going to so I'm going to read the problem and try to solve it. Call Subarray. The following conditions is the number of distinct.
So do you get the definition about the?
I didn't get what is the complete. What is the definition of complete?
Okay.
The number of this. Yeah.
So I'm going to ask you to count the completed subarray. What is complete subarray? So let's see the example. In the example, we have three different numbers, which are 1, 2, 3. So for any subarray that contain 1, 2, 3, we call it a complete subarray.
Complete the whole elements in the array is a complete subarray.
Contain all the distinct elements.
Count all the distinct elements.
So in the given example, there are 4 complete subarray in total, which is 1, 3, 1, 2, 1, 3, 1, 2, 2, 3, 1, 2, 3, 1, 2, 2. They all contains 1, 2, 3.
Okay, my idea is that first maybe we can find all the elements that we need.
Mm-hmm.
And then second we enumerate the start and end.
Mm-hmm.
And then we check if the subarray use all the element.
Okay. Sounds good.
Use all the element use all the elements. So the first step we will need big O(n) to find all the elements in that we need.
Mm-hmm.
So maybe we will have a hash set to put all the elements in the hash set.
Okay.
And then we enumerate. Then we will know how many elements do we need.
Mm-hmm.
Yeah. So we will know the element number. So maybe there are E elements.
Mm-hmm.
E distinct elements in the array. So we get the number here, and then we enumerate the start and end, and then we check if the subarray has E element number.
Okay.
And when we check when we count the elements in the subarray, when we count the elements between start and end, it must have E elements to become the complete array. Yeah.
Okay. So what's the complexity for step 2?
Step 2, the time complexity is big O n squared here because we enumerate the start and end.
Okay. Could you mark the time complexity and the space complexity separately for the step 1 and step 2?
Okay. The time complexity is big O and space complexity is big O n2 because for the headset.
Mm-hmm.
And the second one, time complexity is n squared, and because we have two for loop. Two for loop. And then the second, the space complexity here, because we didn't use any other containers here, so the space complexity is bigger one.
If you don't use any extra space, how could you compare? How do you count the elements within the subarray?
We use count the number in the subarray. Oh, let me think. Oh yes, we can use another hash set.
Okay.
Yeah, we can use another hash set here. So maybe the yes, the time complexity will be bigger on here, because if we count if the element number is equal to E or not, so the time complexity is bigger on the space complexity is bigger on here.
Okay, so I think this solution is easy to write, and before you going to write your code, could you try to optimize this solution?
Optimize this solution. May I know the maximum number of the elements in the nums array?
It could be huge. It could be many.
How many? What is the scale? Would you provide or available?
I wanted the solution could resolve the as many as possible. So
as many as possible.
Yeah, so it depends. It depends on the capacity of your solution.
Okay. Optimize. Let me think.
So in this solution, you have write down the complexity for 2 steps and time and as well as the space. We can see that for the time, the step 2, the time is n squared. So maybe this is a direction that you can try to improve.
Yes. Okay. How many subarrays? Okay. Let me think. Okay. I have another idea. Let's try it.
Okay.
So if we have an answer right here, and we want to, if we find the minimum subarray that can include all the distinct number in the array. For example, in the array, we know that 1, 2, 3 is the distinct numbers in the other distinct numbers in the nums array, right? And if we find that the minimum subarray that can include all the elements, for example 3, 1, 2 here, we know that this is the minimum subarray that can include all the elements, right? And then we can enumerate the boundary here. For example, this boundary can move to left, right? It's move to left, and this boundary can move right. So maybe we can have here. Yeah. So this is the left bound. The leftmost bound can be here or here, and the rightmost bound, the right bound here. The right bound, the minimum right bound is here, and the rightmost right bound is here. Maybe we can take it for take another example for this example. There are many 2 here. So every cut here, every the right can be in every every place like this, right? The rightmost place is here. So we can know that there are two places. For this example, there are two places for left. Two left places. And then we have 1, 2, 3, 4, 5, 6. So we have six right places. So we know that the result is 2 multiplied by 6 and include 12. That will be the ending. Am I right?
You are right in this example, but I don't see how you can use this to solve the whole solution.
The whole solution. So first we.
So okay, let me give you a counter. Let me give you a counter example, and for example, you have 1, 1, 1, and here. Okay. So you can see that we have several 1 in the beginning, and we have 2s at the end of this array, and we have 3 to 1 in the middle.
Yeah.
Actually, it's 2 group of 3 to 1. So can you see the subarray that I select? Okay.
Oh, maybe, yeah.
Yeah, for example, in this subarray, my concern is that some subarray could be count twice or even more times.
Oh, yeah, that's right. Okay, so this idea is not workable. Okay, let me think.
But your idea that if one subarray is complete, you can slide the right pointers as far as you can, because because if it's already complete, you can expand the right pointer of the subarray and it will be still complete.
Oh yeah.
Yeah.
Oh yeah. So we can use a sliding window to solve this problem.
Okay.
So yeah. So we have 2 pointers. One is left and another is right. And if it's not complete, we move the right. We move the right pointer until we make it complete. Right. So in this case, we have like this subarray. It is a complete array, and then we can move the left pointer. And if it also a complete array, we can count it. We can use a counter. So first the left pointer is here, and right pointer is here. We move right pointer to find the first complete array, and then we have counted 1, and then we move left to another. Then the counter become 2 here, and then we move left pointer, and it's still a complete array, so it's become 3, and then we move until the left right pointer, the subarray is not a complete array. Then we move the right pointer, then, and we found another complete subarray. Am I right? So use this. Yeah, we can use this sliding window method to find the number of ways to construct the subarray. So the total time complexity will be big N here, and the space complexity will be, because our container, the worst case space complexity, our container will might put all the elements in the container. So so the time complexity, the space complexity is also big O N here.
Okay. I think you are ready to write your code.
Okay. So sliding window. Okay. So number of ways. Number of okay, the input will be an array. And our container here, we can use a counter order map. Let me think, because we have to determine how many distinct elements here. So we can use this. So we can use an order set here. Insert nums here. So the number of distinct elements E is equal to the size of the hash set.
Okay.
Okay. Then we can use then we can use the map. Yeah, we can use the map here. This counter that can calculate the number of elements. The frequency. Yeah, the number of elements in our sliding window. So then we can do the sliding window here. And then first we put the element into our sliding window. So the counter nums right plus 1. Then we put the elements into our counter. Then if we overlap smaller than right. We want to sorry, let me think. Right, sorry. Then we first we put the element into our counter, and then we check if the counter. Then we check if the check the dictionary. Check the counter here is valid or not. And while it's while the counter is when the counter is the number of the elements in the counter is equal to E, then we can put the elements in the array in the container. So let me think. The check function is to check the counter size. The dictionary the checks the counter size is equal to E or not. Is equal to E or not here. And I will implement this function later. Oh, sorry.
So if it's simply check the size of the counter, why don't you just put it inline?
Because when we put when we move the left pointer, we will also check if the counter size is equal to E or not. And when we move the left pointer, we have to move. We have to do the counter left -1, right? And then in C++, when our counter equal to 0, when we move the left pointer, we -1, right? We decrease the dictionary by 1. And when our dictionary becomes 0, and we will have to remove it. We will have to remove the element, or the C++ will not. It will calculate the number.
Okay.
So I have to. So I have to check another function. I think it will be better.
Okay, I don't see the reason, but you can continue.
I can continue. Okay. Check counter in E here. Oh, it's simple here. Yeah, check function is simple. So while our right pointer is not valid,